So I've been in Taboola for 8 years and counting, and I wanted to present you the research that we did recently on uncertainty estimation in large-scale recommender system. So the agenda for today is we'll talk about a little bit about Taboola, what Taboola is. I'll tell you about the motivation for an uncertainty estimate, why do we need it. I'll tell you how we model it, how we approximate our basic model. I'll talk about two approaches for this approximation. I'll compare them, and then we'll summarize. Okay, so I think Kostya promised we won't talk about generative AI, but the illustrations here are made by Midjourney, so I will give them credit. Okay, so Taboola is a content recommendation engine. Basically, when you browse some kind of a website, like a news website, Ynet in Israel, so you're reading an article, and after you're finished, there are recommended links. If you like this article, perhaps you would like to read these next articles. So in the context of what Uri said, this is the similar items that are recommended. If someone read this article, perhaps he read other articles. And also, it recommends to a specific user. So what happens here is that Taboola is an intermediary between the website, which hosts the articles, the publisher we call it, between the advertisers who want to place their advertisements on the website, and between the users who are browsing the publisher websites, and then they click on the advertisements. So this is the system that's in place here. So what is an uncertainty estimate? Our models are predicting some kind of a probability for a click event by the user. But perhaps we want not just the probability, but also some kind of a measure of how certain is the model in its prediction when it's needed. For instance, in medical applications, perhaps if I get a score of 50% that you have cancer, I would like to know how sure the doctor is. If I'm in spaceflight or in autonomous driving, I would like to know how sure is the model in its prediction. For instance, I guess we've all heard about the Tesla car crashing because they thought the truck is a white sky, but the truck was white. So maybe if the model said, you know, I think it's the sky, but I'm not that sure, maybe this accident could have been avoided. In our environment, sometimes we are buying real estate for an advertisement, and in order to know how to buy it, how to place the bid, we estimate our revenue from that real estate. And to have some kind of trade-off of risk and reward, we can use confidence bounds. So not only the prediction of our revenue, but some kind of interval that bounds our revenue and allows us to mitigate risk and reward. So the question is the score enough? Is our probability estimation is enough? What we estimate is the click-through rate. It's abbreviated as CTR. And our model outputs ECTR, estimated click-through rate. And we recommend models, we recommend items by this ECTR. We put it from some kind of a monotonic function f, and we rank, like Uri said, we rank the items, and we chose the top ranking items for our recommendation. Well, and this means that if I have some kind of an item which got a high CTR but with high uncertainty, it may get an unfair advantage because the model gave it a high score, but it's really not sure, but it will still get in the top of the recommendations. So maybe we want to mitigate that. And if it happens that it means that less suitable items may be presented to the user, it will be less likely to click on them, and everyone loses. The user experience is off because it gets non-relevant recommendations. The advertiser loses because his ad is not being relevant to the user, and the publisher loses his share of the revenue from the ad click event. So let's look at how do we model uncertainty. There are two main sources of uncertainty. Data uncertainty, which is called aleatoric, is an uncertainty that is embedded in the data. It means that it's like rolling the dice. When you roll a die, you cannot know the outcome. It's one of, say it's a 6-faced die. It's 1 out of 6, and you cannot know what will be the outcome. Never mind how many times you will roll the dice. You will still get the same distribution. So it can be reduced with more data. The second type of uncertainty is epistemic. It's part of our learning process. Say we have some kind of a machine learning algorithm. It got a little bit of data, and it's still not sure about how to model the process. But if it gets more data, then it will be more and more sure of its prediction. So we model mostly the epistemic uncertainty. And we chose some kind of a proxy for this uncertainty, how to measure it. We train our model multiple times, as you can see in the infographic. So we have some kind of a neural net. We train it on the same input, or maybe on a sampled part of this input many times. Each time, the neural net starts with some kind of a random initialization of the weights. And therefore, it creates a difference in the training process. Every training run ends in some kind of other local minima, so the predictions will be different. And the idea is the following, that if I'm really sure about a probability regarding to some kind of an input, that never mind how many times I train, all the models will predict the same probability, because this, for this type of input, all of our modeling is the same. But if it's not that obvious, then different runs will end in different local minima and will produce varying outputs. And then the deviation of the estimations from the model will be large. So our model uncertainty measurement is the standard deviation of expected CTR from multiple trained models. So that's our basic metric that we're going to regard during this talk. So now it begs the question, why don't we just compute it and be done with it? So that's the metric. I know how to compute it. Let's do it always. So the problem with this metric is that it's expensive. It means that I need to train multiple models, and then I need to infer multiple times during serving time. So it's pretty expensive. So we want to approximate this metric, and then measure is our approximation good or not. So the first, well, actually the only method that we'll talk about is computing the standard deviation of multiple inferences over a model which contains some kind of a non-deterministic component. What this means is that we've reduced our training time to training only one model instead of training multiple models, so we're saving on training time. The con for this method is that I still need multiple online inferences. Each inference will go over the non-deterministic component and produce a different kind of result. So it's still performance heavy online, but at least we save time on the training part, and I will also talk how we can shave off a little bit more time in online inference. So what are possible methods of adding non-determinism to our model? One method is dropout on the whole network or on separate nodes. For those who don't know what dropout is, I'll just a quick reminder that during training the neural network, we drop all the neurons or a chosen subset of neurons with some kind of probability which forces the network to generalize more. Usually when we do this as a kind of a regularization technique. And during inference, we don't drop the neurons. We just infer as it is. But in this case, we want to infer and perform the dropout still, so that we get different scores from each inference. Another method is a sampling layer, which is inspired by variational autoencoder, but without an explicit encoder and decoder part. I will go into this into greater length later. And the third method is a mixture of local experts. It's a kind of an ensembling method. So we have multiple models that each of them produces a score over the input. Each one of the models is called an expert, and we treat them as random inferences on the same input. The two methods that we're comparing is the sampling method of variational autoencoder and the mixture of local exports. We'll start with describing the general structure of our model. So we predict the probability of a click given item, context, and user features. These are the three main fields of our features. The item features may be item title, item thumbnail, item type, something like this. The context features is time of day in which the ad is displayed, the country from which the user is browsing, and the user features are the user past history of click and browsing history. Each of the features may go into a separate neural net subnetwork. And then together with other features, they go into a factorization machine, which is really similar to the matrix that Uri showed in his lecture. After the interactions, we have a bunch of vectors. They are then summarized by an additional neural network which contains fully connected layers, and they are summarized into a click probability. So that's the main structure of our model. So we'll start with the sampling approximation for a basic uncertainty metric. As a quick reminder or a quick brush on what is a Bayesian neural network, what it means is that usually in neural net we learn discrete values for each neuron. So if we think about them as probability, the probability support is only one value, which has 100% of the probability, and that's it. And in Bayesian neural network, we are learning for each neuron or for some subset of the neurons probabilities. So this means that when we infer from these networks, in these neurons, instead of multiplying by a concrete value that the training process has achieved, we are sampling from the distribution that was learned and then using this value in the computation. And some kind of a quick recap, what is a variational autoencoder? Okay, so that's the part when we talk about a little bit about generative AI, because what it does, it encodes an input x into some kind of a latent space. It learns the distribution of this representation in the latent space, and then it decodes this representation into an output. So this way, when we perform different inferences on the same input, we will get different results, and therefore we will generate different outputs x. So let's delve into a little bit more detail about how do we model it. So the easiest no-brainer choice for each distribution is a normal distribution, unless proven otherwise, every distribution is normal. I think that's a good rule of thumb. So we model it as normal, and what parameters do we compute for a normal distribution? The mean and the standard deviation, mu and sigma. So we learn some kind of a mu and sigma for a normal distribution, and then we have our loss, reconstruction loss. How far is our decoded output from the initially encoded input? This is the x minus fz. This is some kind of a loss. In our case, it's a cross-entropy loss. Also, we're adding a kind of regularization, which is, as usual, to prevent overfitting and to enhance generalization. The way we perform this regularization is by the statistical distance of Kullback-Leibler divergence. We just add it as a term here. And we multiply it by a hyperparameter, which I call KL loss factor. Remember it because I will talk about it a lot in this lecture. And this is the final loss, the final optimization goal. KL loss factor multiplied by the KL divergence and added to our reconstruction loss, which is cross entropy. Okay, so now we have a kind of an approximation to the basic metric. We can compute it. And then it begs the question how to evaluate it. So the method we thought about is just checking correlation between the computed approximation of the standard deviation and the basic metric. So we have, imagine a row of inputs. For each input, we compute an estimate, a standard deviation of the base metric, which results in some kind of a value sigma. And then we compute the approximation of the standard deviation. And if we compute the correlation between these standard deviations over all of our input rows, then we get some kind of an idea of whether our uncertainty metric is actually predicting the model uncertainty. The correlation is a usual Pearson correlation. So we implemented this. We computed the correlation. It was really high. We were really happy and a little bit too happy. And then we thought, if you do something and it works really well at first, you've probably made some mistake. So the graph here is, on the x-axis, you see the score itself that we computed, the estimate. And on the y-axis, you see the standard deviation. And it looks pretty much the same both for the base metric and for our approximation. So can anyone spot a problem with this graph?
There's actually a straight line. Not normal distribution.
So it's not that straight, actually. Well, maybe it's a little bit hard to see here, but actually it follows a kind of an arc pattern. So you can see that towards the middle, towards the half score, the variance of the standard deviation grows and also the value grows. So there's a correlation between the score and the standard deviation. And then if I compute the same scores with two different methods, of course I will get a correlation because they follow the same pattern, right? So it's not really predictive of whether I have a good uncertainty estimate or not. Yes?
Can you go a bit back?
Yeah.
So in this slide, you're evaluating your approximation method, right?
Exactly.
So the base STD is calculated like old school with multiple models.
Exactly.
Yes.
But you will need to do this evaluation for any model you will train.
Exactly.
So
Yes.
you save nothing. Like, you will never know your evaluation, the quality of your approximation model until you will retrain heavily, expensively.
Yes, of course, but you only evaluate the method. I mean, if you evaluated the method...
Evaluation is highly dependent on the model and on the data. You cannot generalize the evaluation method. So in the evaluation method, you can be very successful on one client or one type of users, and you will change something small, like you will add layer to your neural network or something, and the approximation method will totally be off.
Perhaps, yes. So maybe it's a good idea to test this from time to time. But our assumption, if this method works, then it will work for newer data. Perhaps it's true, perhaps it's not. And I think it's a good idea to test this from time to time, to test that the correlation hasn't gone down. It's a good idea. But our assumption, of course, in this evaluation, that we evaluate it once, we validate the method, and then we say, OK, this method works, and we can do it online. We'll see. We'll see if it works. So when we see this problem, we can kind of zoom in into different regions of the score. We can see that here in this region from 0 to 0.4, we have a clearly distinguishable linear pattern, just this diagonal line. But if we go to the score bucket between 0.4 and 0.6, we can see that it's already kind of a straight line. It's not that dependent on the x-axis. And perhaps it's best to measure the correlation only there. And actually, it makes sense, because the score half is basically the model saying, I don't really know if there's a click or not. This is the place to say that we're training on balanced data set. We have a label of click and non-click. And there is an equal amount of both of them in the data set. So the average score is half. So saying half is like, I don't know. But maybe it's really sure of that half, and maybe it's not. So that's what we're trying to measure. So the estimating the uncertainty is hardest around half. So we will measure our performance around half, and there we will see the truth. So here we can see in the right plot the correlation by score bucket. So you can see that in the extreme buckets, the correlation skyrockets. It's really high, 0.7, 0.6. But it's not really informative because there's a linear pattern that both the approximation and the original basic metric follow. So probably the correlation is derived because of this. But in the middle bucket, therein lies the gold, because this correlation is true. Because you can see here the scores distribution in this bucket. It doesn't really follow any distinguishable pattern. So any correlation that will be computed on this bucket is because our uncertainty computation approximation is probably good. So that's the idea, evaluation on the hard segment of the scores. Now I will talk a little bit about the hyperparameter tuning of how important is the KL regularization loss. So we performed a few experiments, few extreme ones, and something in the middle. In the extreme one, we set the KL loss factor, which I remind you is the number that we multiply the KL divergence in our total optimization loss. So here we literally multiplied by 1,000,000. We say it's really, really important. It's really important for me that the distribution, this latent space, will be really close to standard normal with 0 mean and 1 standard deviation. And here we can see the x-axis is the training process, the training steps. And we can see that the regularization term goes down because we said it's really important. In the right plot, we can see a case when we said it's almost not important, the regularization. We just want you to compute some kind of good distribution that will model this latent space. So we can see that this value goes up because it's not that important. And in the middle, there's a sweet spot where this term went up because we wanted to model our feature correctly. And then it stopped and said, okay, my feature is modeled good enough. Now I want to satisfy the regularization condition. And there the term goes down. And we will see this in a little bit more detail, the training process. So here is the case where the regularization is really small. It's not that important that the distribution will be close to standard normal. And we can see the z-axis is the training process. So it goes from top to bottom. The training process goes like this. And we can see the distributions of the mean and the log of standard deviation over time. So we can see that the support gets wider for both mu and log sigma. It means that the values, we're getting a wider range of values that represent our latent space because we can allow it. We want to allow this flexibility because we are not really bounded by the regularization here. On the other extreme of only the regularization matters, we can see that during all of the training process, the distributions stay peaked at 0. So 0 mean, 0 log sigma. So it means sigma equals to 1. So it means basically says I've canceled this feature. This feature is just normally distributed, and I don't have any information about the feature. But the nice part happens in the sweet spot, because we can see that in the log sigma, the support got wider initially to represent the wider range of values, but then it got narrower because we said, okay, we need to regularize. We need to make it not as far from normal standard distribution as it went. So this exactly correlates with the learning curve, what we've seen of the regularization term. So I think it's kind of a nice infographic for how to understand intuitively how does the regularization affect this process. And also we've seen it as a kind of a feature of, a kind of a proxy for feature importance. That's everything about the sampling approximation. Any questions so far? Yeah.
can't you learn this feature by saying something that the KL divergent factor need to the KL divergent part need to be 10% of the score, something like that? Can't you do something like that instead of just saying KL divergent factor equals that?
Learn it how?
Start and do some testings, and you will get the KL divergence score plus the factor, and you will get the distribution score, the other part of the score, and you can say the total score is needs to be 10% KL divergent, 10% the similarity.
Yeah, but that's exactly this 10% value is exactly what we're tuning here, because we're not sure how important it is. It's just in any case of regularization, you need to test how much it affects your generalization, how much it hurts the precision. So it's kind of a tuning process. But actually, you know, it's one direction that we could follow, kind of incorporate the uncertainty into the optimization loss. So it was also a direction that we considered, but it didn't go to fruition. But it's still, you know, an idea. Just instead of learning an uncertainty estimate, just incorporate it into your optimization loss, and then it will be learned by the network. But we didn't get that far.
Why don't you change the KL divergent factor through the training? Start with saying KL divergent doesn't really matter, and as long as you go through the training, the KL divergence matters more.
Of course, yeah. It's an ideally it's a good next step, of course. Just like you do the same scheme with learning rates in general. You start with a big learning rate, and then you go smaller as you're getting closer to the minima. So yeah, it makes sense.
Yeah, it's a bit confusing because the amount of global minimas for a neural network is infinite. So you can have a distribution, you can have a variance of the representations, but they may actually all be rotating around global minimas, across global minimas. So what meaning does the variance have in this context when they're all essentially the same representation, just rotated?
I'm not sure I understand. The multidimensional space you've described, I'm not sure I understand.
Yeah, the optimization landscape of
Yeah.
that network. You can rotate across it and you will have essentially the same neural network implemented with different weights. So if you have variance there, it may be a false summary metric because you're rotating around something, you seem to get variance, but there's no actual difference.
But it's not, you don't pass from one local minima to another necessarily by rotation.
Necessarily pass across global minimas by rotation.
Between local minimas. Global minimas.
Global minimas of the network. Also local.
Global, you have one.
Yeah, global you have one. I'm not sure.
Infinite on over-parameterized neural networks. You can overfeed the data in many different ways.
Yeah, so I'm not sure how to, but it's an interesting point. Okay, any other questions? So let's go to the second method. The second method is a mixture of local experts, which means the following: that we take our model and we replicate some kind of a subset of the neurons in the network, and each one outputs a different output. We call each such part an expert. Each such expert has its own loss, cross-entropy loss, and all of these losses are combined by linear weights, which are learned also by an entity called the manager. So the manager combines in a weighted average the losses of each expert. It constructs a single loss, and this is the optimization loss for the model. So now you can see that each expert has his own output, and we can treat this output as one inference of our model, and we compute the standard deviation between them. So generally, mole, mixture of local experts, leads to sparse solutions, meaning what does the local mean in the experts? It means that each expert is an expert in his own field. For instance, I get, I don't know, items on a phone platform, and there comes the phone expert, and he says, okay, I know how to compute scores on this subspace of the feature space. So in order, so it's not really good for us, this sparse expert property, because we want all of the experts to participate, so we can compute a standard deviation over all of the experts. So we add a load balancing regularization term to force the experts to be more or less uniform, the weights that the manager gives them to be more or less the same, so they all participate, and then we can compute the standard deviation between these scores, and it will be meaningful for our purposes. So we did this, and we compared here 3 different approximation methods. The first method is the best method that we came up with using the variational autoencoder method. And our metric is the correlation of the standard deviations. In the case of the mole representation, it's a weighted standard deviation by the manager weight. Here, we're computing mole score over replicating only part of the network. And here, we're replicating the full network, essentially going back to the base case. So in the base case, of course, we see great correlation because it's basically making the same computation. So we cannot hope to achieve it through any other method except training multiple models. But we can still see that the correlation of the mole experts that are replicated through the fully connected layers is better than the variational autoencoder which samples all of our categorical variables with some kind of a low but non-zero KL loss factor. So why do we need this? So it saves us some time in inference, because inferring, doing all of the subnetworks and then all of the factorization machine interactions once, and then doing only the dense layer stack for each expert, it saves time. Compared to inferring the entire model multiple times. So this is an efficiency concern. We want this for efficiency online. And we can see that all of the approximation methods, even the sampling one, show significant correlations with base uncertainty estimate. And I remind you, it's not general. It's in the hardest case of the scores that are around half, around the score that says, I don't know nothing. So for the sampling configuration, if you want to try it out, sampling more features worked better. So we sampled all of the categorical features, and we did a pretty low weight on the KL loss factor. And in the mole configuration, we took 20 experts. I guess more will be even better, but that's probably what we can afford for now, performance-wise. And with a really high load balancing factor to enforce the uniformity of the experts. It's still hard performance-wise, but we're testing it online and it shows promise. So that's it. Thank you for your time. And it's time for questions. Yes?
Yeah, I have a question. So having the asset emerger, can we actually distinguish between aleatoric and the epistemic component to, for example, to understand if it makes sense to have more data to explore this context better and so to get more data? Or maybe we know that the epistemic is really low in this case, and that doesn't really make sense to get more data and to explore this more.
Well, I'll just repeat the questions. The question was, can we, using this method, distinguish between aleatoric uncertainty and epistemic uncertainty? And my guess is not, because because we do this multiple trainings, we see the variance, and we don't really know where does it come from. Is it from our model or from the data from the uncertainty inherent in the data. That's my guess, that we're modeling here both model uncertainty and data uncertainty. That's how I see it, but maybe, yeah.
How many experts are there?
In our current implementation?
Yeah.
Now 20. Of course, 20 samples for distribution is not enough, but that's what we can afford for now. Any more questions? Yes.
If you are saying you're using 20 models, can't you use a smaller model because you are using 20 models and do an aggregation of them?
So we're actually thinking about that, because it seems that the model size doesn't help us as much as the experts amount. Yeah, so it's, I mean, yeah, it makes sense. It's an assembling solution, so it makes sense to aggregate many smaller models.
When you calculate the standard deviation according to the estimation, is it globally per item or per item per user?
It's per data row, so it's per item, context, and a specific user visit on the website. Yeah, maybe I should have said that each input row is a specific user impression of the website. Okay, thank you for your time.